Hi, welcome back to Algomet, your friendly guide for tricky algorithms. In this video, let's try to understand the two's complement representation of binary numbers in our usual, most basic, fundamental, step-by-step manner. Are you ready? Let's go. Hi. In the introduction, I mentioned that we'll look at two's complement representation of binary numbers. But let's begin with decimal numbers. Why? Because when we start to look at the binary representation, we start to look at the actual semantics of the representation, the transformations that we can do, and then we lose the intuition a little bit. So let's just look at plain simple decimal numbers that we are comfortable with. If you pay attention to the right side of my screen, we have the number line. We have 0 at the origin, and then we can count up as much as we like. We can, for example, here we have a billion, and we can count down a negative million, a negative billion, and so forth. But this is in theory. In reality, however, our ability to keep track of numbers as they grow in size with a fixed precision. For example, let's say here we want to be able to also have precision of 1. So it's 0, 1, and so forth. Right. So that's what I mean. Uh, we are limited by certain factors. In our mind, we can think of any big number, but if we have to represent it in an external form, uh, we are limited by certain limiting factors. For example, over here, if we consider our ancient ancestors, when they were counting, they were probably limited by this factor, the number of fingers that we have on our palm, 10. And then as the civilization developed a little bit, maybe this limiting factor got pushed, got stretched. Maybe we were using rocks to keep track of things, and then we were limited by the number of rocks that we had around us, or the number of rocks that we could carry on our shoulder, or perhaps the size of the bag that we have to hold these rocks in place. As we grew better at inventing means to circumvent or to address this limitation, we at some point in time we reached paper, but still we are, though we have a far wider range, we are still limited by the size of the paper and the number of pages that we can have in a book. So there is always going to be a limitation. It's just it gets stretched, and the number of problems that we can solve uh, widens, increases. But so when we are confronted with this problem of the limitation in how large a number we can represent, what do we do? How do we address that? One way is like we really do not care once the number goes over a uh, certain threshold, or maybe the maximum that we can represent. If you look at my screen here, here we are using 4 digits to represent something, and once it goes from 0 to 9999, we just don't do anything, because we are like, okay, anything over 9999 is as good as 9999. It's like infinity, or just high enough in the record, and beyond that we really do not care. An example of this is like a child saying that they have a million gazillion of their favorite collectibles. So they really do not care how many exactly they have, but the bottom line is like they just have enough of them. So this is saturation. This may help us in certain situations, but in certain other situations, it may be a bit problematic. Let's see why. So let's say if we are using two numbers, we are using two numbers to count the distance and the time that this motorcycle is traveling or has traveled. So we can use the ratio of the differences of distance and time to estimate its average instantaneous speed. Now, if we start to saturate, And if we let's consider that we are representing the number of meters that this motorcycle has traveled, and it's going downhill here. Once it crosses 9,999 meters, we saturate. So what happens, like after about 10 kilometers, we don't get any more accurate estimates of its instantaneous speed, because we saturated this high value. The difference will be zero, and then we our whatever design that we have done is not helping us beyond 10 kilometers of initial travel. So to get around this problem, we need to think of some other means. So what would we do in this situation? What would you do? As you have correctly guessed, you would just wrap around. So once you reach the limiting number here, 9,999, you can just wrap around and go back to zero. So since you are just taking the differences, it would not matter. And if you are careful enough to take the absolute of the differences, you will always be representing uh, the an an approximately accurate estimate of the instantaneous speed of the motorcycle. Or let's say, even otherwise, there may be a small portion while we are transitioning from this 9,999 to back to zero. We may not have a correct estimate, but that's okay. After that, we have a correct estimate of its speed. Now, this is a hypothetical example, right? If we want to look at a real world example of where we do this wrapping around, can you think of one? Yes, that's correct. The clock. The clock is a very good example uh, of counting and wrapping around when we reach a certain limit. So, for example, here we can consider the limit as 12, and once we reach 12, we go back to 1. So there is no 13, at least in these clocks or many wall clocks that we have. So here, what matters to us is like relatively, when we have a certain point in time, we know the origin it's at 12, and then we want to see like how far off we are from this particular origin in either direction. So when we go clockwise, the convention is like we are considering that the time is moving in positive direction, and for example, I mean, if we want to reset our time, or if we want to just if we want to estimate as 2 hours from now what the time was, we could just imagine the clock hand going backwards anti-clockwise, and where it would be, for example, 2 units from here, it would be 1 o'clock. So when we are adding, we are going clockwise. When we are subtracting, we are going anti-clockwise. This is how we are doing addition and subtraction uh, in the clock. Now, since we have a wrapping around mechanism here, what would happen when, for example, if I want to subtract 3 from 11? So I would have to go anti-clockwise, 1 unit, 2 units, and 3 units, and I end up at 8. However, since we are wrapping around, I could also go 12 minus 3 units forward direction. Let's see if that is correct, which is 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So, and then I end up at the very same location, which was giving me the value of 11 minus 3. So I can move either 3 units backward, or I can move my limiting factor, right? My limiting factor minus the 3 units in the forward direction. So 12 minus 3 is 9. Let's do this one more time. It's fun. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have two ways to do subtraction uh, when we are wrapping around. So this whole wrapping around is called as uh, modular arithmetic, but wrapping around is also okay, right? So now you may say like, why, I mean, why do I care? I can just go anti-clockwise when I want to subtract. Why should I just turn around all the way back and come back here? There may be some technical advantages of having a different method to do your subtraction. So let's see, let's just hypothetically think of one such example. So let's get to our hypothetical example of why we would benefit uh, by having a means of not changing the direction of rotation when we want to subtract. So whether we want to add or we want to subtract, we love the clockwise. I don't know, we don't like anti-clockwise at all. So uh, what could be a case, such a case, right? So this is highly hypothetical, but just for the sake of example, I'm presenting it. Let's say we are using our this whole rotational, mechanical, whatever thing to do some addition, right? So imagine you have a motor here, which is rotating this hand, and then it shows us some output value, and maybe we have some other piece of equipment where we could feed in uh, the value that we want to add, and I mean, or our input value, and whether we want to add it to the current value of this pointer, or whether we want to subtract it, and maybe a push button, say execute, right? So given that we have such a weird equipment, and imagine the user has entered some value and said add, right? So add 3. So the pointer is at 3, the motor takes that input, and then it rotates it uh, 3 units clockwise, 1 2 3, and then we are at 3. Now another user comes in, and then here he says, he or she, the value is 2, and subtract. So if the motor was capable of moving this hand in the anti-clockwise direction, so it could move it 2 units back, and then the user would get the answer. Oh, 3 minus 2 is 1. Great. But what if it is costly to implement such a motor, which could do both anti-clockwise and clockwise rotation? Maybe it is more efficient, or cost effective, or space effective, or weight effective, whatever, effective in one or the other way. Or if we don't have to do this bidirectional motion, and then we if we can live with somehow with just unidirectional motion. Anyway, we are wrapping around, right? So it does not really matter. It's not that it's not flat earth, it's a round earth. So you go enough due north, you will start to go south. um, so I think now we have motivated ourselves, right? As why we need this additional ability to be able to subtract in the same way that we do addition. When it comes to digital circuits, of course, we can just have one circuit, right? And then if we can somehow calculate, but there is a catch here, right? So when we want to subtract 2 from 3, we need to go back 2 units, or we have to go forward 10 units, correct? uh, for the sake of fun, let's do it one more time. So from 3, so 1 2 3 4 5 6 7 8 9 and 10, and we are at 3 minus 2 is 1. So we need some way to figure out that if the value is 2, and if what we want to do is subtraction, we need to be add 10. Add 10 is same as subtract 2. So we need something that can evaluate this for us. So if that something is easier, uh, cost wise, weight wise, whatever, some feature wise, it's more efficient than having the ability of the motor to do this bidirectional motion, then choosing this way of doing subtraction by means of adding another equivalent number uh, would be a viable option. So now we need to have a name for that number, right? For that magical number, which is different for each value that you want to subtract. So for 2 it is 10. For 3, what is it? For 3 it should be 9, and so forth. So this is like the number that we want to subtract. We have to subtract it with the maximum number in our representation. So the word we give it is complement, because if we add them together, what will happen? We will arrive at a uh, limiting number, or we will come back to origin. So here we go back 2 steps, correct? Because we take a full circle, and the circle represents the size or the range of numbers that we have. So you have 2, and then anti-clockwise 2 is same as clockwise 10. You do 10 plus 2, you are 12. And then anti-clockwise 3 is same as clockwise 9. You do 9 plus 3, it is 12. And hence, since they complement each other, we call that number which we need to add for a given number x, that we would like to subtract, is called as the complement of x. So now intuitively we understand what is complement, right? It's just that. So we need not do that whatever uh, flipping of bits and such. Now let's do a small adjustment here. Uh, if 12 is the origin, if this particular number here is origin, what can we do? We can I can call it 0, right? This is not a clock anymore. So we start at 0 in this convention. We are starting at 0, we are going from 1, and then we are arriving at 11. So if we start at 0, and the number of numbers that we can represent, if it is 12, the maximum number is the 12 minus 1. If we start at 0, if we start at 1, it will be 12 for sure, right? So here we get the concept of uh, the total range of numbers, or the maximum positive number that we can represent. Now let's talk about negative numbers a little bit. Interesting part, right? So 11, we can call this position either a clockwise 11 or an anti-clockwise 1, correct? So either we can take 11 units of clockwise movement to get to 11, or 1 unit of anti-clockwise movement to get to 11. So it's our choice. We can call it 11, or what can we call it? We can call it minus 1. In a similar way, now we can call this as positive 10, if we consider it's the direction of motion in a clockwise manner from origin. We move 10 units, we get to 10, or we can move in an anti-clockwise manner and we get to this particular position. Now if we want to represent it that particular way, then why not call it minus 2? And you get the picture. So this is minus 3, minus 4, minus 5. Interesting. This can either be 6 or minus 6. So either way is fine. When it comes to binary numbers, we want to keep it minus 6. When we will do a power of 2, limit this the number of the numbers that we can represent to a power of 2. Slowly let's transition to binary numbers now, because we have a fair understanding of what a complement really means, and what a negative number really means. A negative number, just there is nothing fancy about it. It is the direction in which we are doing our increment in our modular arithmetic. So from the origin, if we are going in the backward direction, then we are our convention is that we have a negative number. If we are going in a positive direction, then we have a positive number. So now that we have negative numbers, let's try to quickly, uh, let me just quickly make this a, uh, let me adjust this clock to a power of 2, and then we will continue with our transition to binary numbers. So here is our big transition from decimal to binary representation of numbers. We have now the clock has more numbers. Instead of 12, we have 16 numbers because that would be a nice power of 2, and that's the usual way in which we represent numbers in digital computers, right? So we have here numbers going from, let's say if we just have 4 bits, right, then we can represent numbers from 0 to 15, and their binary equivalents are given over here, all zeros and then all ones. We can choose whichever way of representing the numbers, but this is one easy way, right? So you do this, what do you say, sum up. We have each of these is a power of 2, and then the last one here uh, is 2 cube, and this is 2 square 4, and this is 2, and this one is 2 power 0, right? So we have from 0 till 15. So now uh, everything is same, nothing really changes from what we discussed with the decimal representation. So let's just directly go and start to do some uh, transform some of these values which are closer to the origin as negative numbers, right? Which we did with the decimal representation. So we have this 0. Now the value 1 to the left of it, or in the anti-clockwise direction, becomes -1. This becomes -2. That becomes -3. So 12 is same as -4. 11 is same as -5, and 10 is same as -6. 9 is same as -7. And now here is, oh sorry about this, yeah, now here is this interesting point, right? What do we do with 8? Shall we leave it at 8 or make it -8? We can make it -8 because that gives us the advantage. If we look at this pattern, right? So the last or the most significant bit is 1. So if by convention, if we also take this bit representation 100 as a negative number, so if we just see like how far off it is in the anti-clockwise direction from the origin, it's easier for us to do certain decisions. For example, to check if the number is negative or not, because if we then we can just rely on the fact that all negative numbers are going to have their most significant bit as 1, and then that will be one problem less for us to break our heads with. So this is one simple representation, and this is the reason why when we are using a negative convention in our number representation, we have the range from 2 power whatever is the maximum. Let's say if we are using m number of bits, then 2 power 2 power m minus 1 is as negative as we can go, and 2 power m minus 1 minus 1 is as positive as we can go. So here we our m is 4, m minus 1 is 3, 2 power 3 is 8. So our most positive number is 7, and our most negative number is uh, -8. So this probably has what do you say, clarifies the various design decisions that are made. But intuitively it is just when we are thinking of a number as a negative, then we we are just looking at the direction, like how far off it is from the origin in an anti-clockwise direction, right? So you start at the origin, so origin is somewhere in the middle, and then you can go either clockwise or anti-clockwise, or whichever way you want to call it, and then you lead into positive numbers. And if you allow a little bit of overflow from the most positive number, this is probably one of the pitfalls that people fall into if they do not visualize uh, numbers represented in two's complement form in this particular fashion, where they may think that after the most positive number, if you add 1, you will get to minus 1, but you will actually get to the most negative number, which is minus 8. But that is very clear here from the visual representation of these numbers. Another part is how do we arrive at the complement? So, for example, 5, right? So, how do we arrive? For example, 2. If I have to subtract 5 from 2, I have to go 2 units in the anti-clockwise direction. And looking at our convention, if I want to subtract uh, 2 by actually going in clockwise direction, then the number of values that I have is 16, and then 16 minus 2 is the complement. So I have to move 14 spaces in the forward direction. 14 spaces in the forward direction uh, to reach the answer. 5 minus 2 is 3. So let's do this for fun. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right? So 5 minus 3 uh, is still 2, even if we do 5 plus 14. So 5 plus 14 is same as 5 minus 3 in this representation, where we are wrapping around after 15. We are coming back to 0. So now if we have to subtract 2 from 5, right? So 5 minus 2 is 3. So we just go 2 units in the anti-clockwise direction. If we have to go in the clockwise direction, what is the complement? It is just minus 2, right? So we can just read off the value. What is minus 2 here in our representation? It is 8 plus 4 plus 2, it is 12, right? So we can just go 12 units in the forward direction. Sorry, this is not 12, this is 14. 8 plus 4 is 12, and then here we have one more 2. So we just go 14 units in the forward direction, and then we will be at our result, which is going 2 units in the backward direction. So for the fun of it, we can do it, but I think now it is more quite intuitive for us, right? 14 plus 2 is 16. So we end up at this same value if we go 14 steps forward. So, but for the fun of it, let's do it very quickly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So, even this way, we arrive at 3 as the answer. So the only thing now is from 2, how will we get to minus 2, correct? So the representation that we have for 2 is 0, 0, 1, 0, and the representation that we have for minus 2 is this triple 1, 0. Now this part is mechanics. How we can get to minus 2 from 2 is you just you flip the bits here. If we flip the bits, let me just take this example here. If we flip these bits, we get 1, 1, 0, and 1, and then we can just add 1 to it. Now if we add 1, what will happen? We have a 0 here, then we have a carry. So yeah, So we have a, let me align this properly. So we have a 0, then because we have a carry, we get a 1. We get that carry goes back, and thus we end up at the complement, which is this 1110. So basically, what we are calculating whenever we are saying 2's complement or whatever, we are just calculating the natural complement of numbers that wrap around. Uh, However, because when we study the numbers and the binary representation, we somehow transition from this so-called ones complement, and then we go to the more advanced two's complement. And here is where we kind of may lose the intuition of it a little bit. But what we are doing right now, implementation wise, is the most natural complement that can exist. So this is the complement. So this is what I wanted to impress upon you in this video. There are several further aspects to it which are quite intriguing. For example, you can swap two numbers. You might have had this as one of the trick questions when you started programming. You have like two values A and B, and you can swap. Can you swap them without using another temporary value? So I would want you to think about it. Let us say you want to. Let's just reset these back to the positive representations. Let's say you have two numbers, 14 and 15, and you want to swap the values, right? Now you know that if you do this, if A is 14 and B is 15, now you know that, sorry about this, yeah. Now you know that when you add 14 to 15, you will go over, you will wrap around. You know, you do this A equals A plus B, and then from that you subtract A, you get B, and so forth. That's how you do the swapping, right? So I want you to think about it and see how would it really work uh, when we are dealing with these numbers, which would actually wrap around. Would we get correct results? Can we still use that algorithm, or do we have to use some other temporary variable to swap the numbers? So, with this puzzle, let's conclude the discussion here. Thanks for watching.